Okay, cool. So, nice that you're here, despite of the ID talk. So, what are we going to talk about now? We're talking about biometry, but why do we want to use biometric in identification systems at all? We've got quite a bit of history there. And we'll tell you about biometric characteristics and the challenges involved there. We'll talk a bit about similarity learning and two approaches. One approach is using newer technology like neural networks, and the other one is doing classical like computer vision things and classical programming with feature engineering. And then we'll get a bit into open source software because there's really great stuff out there to do biometric identification within just a few days. So our first prototype was made in like 4 days, and we had a registration and identification app. So there's really a lot of great stuff out there, and we'll demo it to you too. Okay, so.
I've got my own mic, so thank you, Mathias. So yeah, how did this project start? It was a charity that came to TNG, and they wanted to explore whether they could develop a biometric identification system. Why would a charity be interested in this? Well, they provide aid, material aid, and they're really the sort of charity that provides aid in very poor areas. And so it's really quite critical that they have a system in place that avoids people registering multiple times and getting aid fraudulently. So they're interested in a cheap biometric identification system that needs to be employable in the field, so it needs to run on very low spec hardware, ideally a mobile phone. So that was our brief, and so a group of at TNG then started to research potential technologies for this at the winter retreat. And they already came up with a number of really nice open source packages that we then started to incorporate in a prototype that we built back in February. And as Mathias said, with those nice open source packages, you can really get to a result in really quite a short space of time. So we'll, in the talk now, we'll both talk a little bit about these software packages, but also about the underlying technologies and concepts.
So there are a lot of biometric characteristics out there, and we want you to provide us with a few of them.
Voice, face,
yes?
blood, fingerprint,
oh, wow.
footprint.
Oh, so you're in forensics?
Isn't there something about the ears?
Ah, very good.
Yes, yes. Ears characteristic too.
Iris.
Yeah, iris is great.
Full face.
Yes?
DNA.
Yeah. Right, movement like gait is also characteristic for people.
Mm-hmm. I think this covers almost
So,
everything that
yeah.
we thought of as well.
So you're quite informed. That's great. There are lots of other characteristics. Skin may be another characteristic, but skin also changes over time. So you need to be careful a bit. But some characteristics can be taken as a secondary characteristics to identify people, really. Okay, but one of the challenges really is liveness detection. Because when you just take a picture of someone, a picture of the face, you cannot really say if he or she is really alive or not. So most of the systems nowadays need to detect this somehow. So face identification is a 3D identification process, for example, but then you can still build things like masks. And for this one, you could also go one step further and take a short video sequence. Because on video, you can see very small changes in redness in the face because your blood pumps through your face. You can see this on a camera. Okay, so what about data? All the time when we want to prototype some system, we need input data to work with. Fingerprints and iris data is really hard to obtain. NIST even stopped providing you with this kind of data. And much of it is also only available for research purposes, and you need to sign very strict contracts to get the data, actually. But faces and speech are really easy to acquire because there are really large face databases out there like Mega Faces or MS Celeb, 1 million celebrities, There's Facebook, you could grab images from there or just don't, because it's not really GDPR compliant. And speech can also be obtained. There are a lot of data sets like the LibreSpeech data set. It contains about 1,000 hours of spoken text from different people reading their books. And there's also a common voice project from Mozilla, where they also capture voice. And using this data, you can then start to prototype your system and to train it. Okay, but beware of the restrictions of the data use. You cannot use it for everything.
Okay, then we would like to spend a little bit of time speaking about one of the key concepts in this area, and it's a concept that underlies most of the, let's call them, modern approaches to biometric identification. And, well, it's called either similarity learning, sometimes it's referred to as metric learning. The idea is, well, what we'd ideally like to be able to do is we see an object, say a face, a single time or only a few number of times, and then when we see it again, we are able to re-identify it. Now, if you think about how much of the deep learning algorithms, how these tend to work, or your typical classifier, you throw lots of examples into it to come up with a reliable classifier. So this is a slightly different problem here. So what I've just described, this is sometimes referred to as one-shot or low-shot learning. And to be able to achieve this, we still use a lot of data, but not the data we ultimately want to classify and re-identify, but database of other faces or the objects we want to classify. And we use that not to ultimately classify the faces, but to learn what makes a face, two faces similar to each other or very different to each other. So we try to learn a distance between faces, and this distance ideally is small between like faces and is big between different faces. So if you, I mean, in a formal way, you can pose this problem like this. You've got two examples. It's still a classification problem, but it's not a classification problem between individual objects, but it's a classification problem for pairs of objects. So you try to classify pairs of objects into a similar and dissimilar category. Okay, now this sort of fits quite well with deep learning approaches. And if you combine the two, you can really achieve quite spectacular results. And face recognition is really the showcase for this sort of technique. So deep learning plus metric learning is really the way to do face recognition. And this is sort of a timeline that shows the development of face recognition over really not that long a time ago. So if you only going back about 20 years, the face recognition rates on this particular data set were still quite low. So this was using more or less classical methods. And it improved, but really over the last, say, 10 years or so, it sort of exploded with the advent of really deep image recognition algorithms, but also this combination of these deep image recognition algorithms with metric learning. And we've really gone from very poor accuracy rates to 97%, and now it's more like 99% or 99% plus on this particular data set. Labeled Faces in the Wild, it's a data set of celebrities in various situations. Then, oh, sorry. Oh, yeah. Then how does this work, this combination of deep learning with metric learning? Essentially, you still try to learn a traditional classifier, but you then don't use you're not so much interested in the classifier that you would normally be, but you use the features that you generate by training a classifier to then create an embedding of the objects you're interested in, faces in our case, and then use these features, this embedding, to vectorize, if you will, new faces and compare new faces against each other. Now, one little complication here is that whereas in a simple classifier, it would be enough to learn features that are separable. So you've features where you can draw a clear dividing line, a clear threshold, if you will. In order for this metric learning, similarity learning concept to work, the features we want to learn really need to be discriminative. And what we mean by this is that not only do we need to be able to draw a separating line, we also need distances within a class to be short and distances between different classes to be large. And Mathias will now explain how this can be achieved.
Okay, so one of the training strategies is using a Siamese approach in neural networks. So first of all, you need to mine pairs. You need to provide the network with similar and dissimilar pairs, and you need to provide them in a balanced manner. So this involves quite a bit of work, and then you run them through you run two examples through the same encoder model and get some embeddings out of it. And then you can compare the embeddings because they are just two vectors. So you can think of differences like angular distances or just L1 or L2 distance between the vectors. And when the distance is quite low, you have a very high similarity score, and when the distance is getting higher and higher, the similarity decreases, conversely. And you can now base your loss on the distance and compare it to your class label, and then do just a classification problem and say, hey, when I've put two similar instances into it, I want the model to predict something with a very low distance, and when you put dissimilar pairs into it, you want to have a distance that is higher than some margin. So therefore, there's a special loss function involved. For example, in this case, it's called contrastive loss. And what contrastive loss does is it pulls the representations of similar pairs near to each other, and it kind of repels the representations of dissimilar pairs. But for that, in order to work, we need to mine those pairs of similar and dissimilar pairs. And so training strategies evolved over time. And on the left side here, we can see just a normal softmax cross-entropy loss. And in the softmax cross-entropy, we can see that classes are separable here. We can separate them. But the distance between different classes is sometimes very small. And the inner class distance is much too high. So one method to compensate this is to use something called center loss. And in center loss, you've got a term where you compute class centers per batch, on a per batch basis, so you don't need to mine pairs or triplets. And you basically pull those representations together to be more similar. So you penalize it when it's spread out like this. And then you compare the softmax with the center loss, and you get representations where you've got very, very similar representations for similar objects, and all of them are really separable by quite a margin. So you've got a bigger distance between dissimilar classes here.
Mm-hmm. And yeah, well, this slide essentially summarizes what Mathias just explained. So this is a short timeline of how these training strategies for similarity learning in a deep learning setting have evolved. So as Mathias has said, initially people just tried to use a simple cross-entropy loss function for this, which has got the problems that features learned are not discriminative. Then pair and triplet mining started, and then we've got the center loss function, and what comes after are essentially developments from the center loss function that include angles and things. But this is really the latest concept. Maybe historically interesting, why wasn't the center loss developed before the pair and triplet mining? Because in a sense, it's much simpler, right? When you use the center loss, you still have got the same architecture. You don't have to create a Siamese network and calculate the distance and compare, and you don't have to come up with to mine triplets and pairs that cover all the the distances between all the different classes. Well, the problem is really the way neural networks are trained, and that's typically using stochastic gradient descent, which means that you train in batches. You never, in a single training step, you never have all your data set available, which means that in a single training step, you don't really know where your center is. So somebody had to come up with a way of learning these centers as you go along through your training, even though they are not available in an absolute sense at any given training step. So this is why this only came after triplet and doublet pair mining.
Yes, and now with the large margin loss, we really get quite an accuracy boost again. So now face re-identification is at rates of 99.7% and growing. Yeah. Okay, so let's get a bit into code, because here at TNG we are really into coding stuff. And let's take a slightly different example to see that the approach is very versatile and you can use it for any biometric learning thing. So in this case, we want to do some speaker verification where we've got voice data. So voice data is one-dimensional. We've got just this time axis and we've got values over the time. And we can come up with a neural network that is quite standard, not very efficient in terms of parameter usage, but the architecture is quite standard. You do a one-dimensional convolution in this case, do your batch normalization to get values into a numerically stable range, perhaps apply some dropout for regularization, and do some dimensionality reduction. And then you go along, increase the filter size, and so on, and so on. And then put a dense layer on top of it, and then you get a feature vector out of it, which you can later on compare to another and build a distance upon it. So this is our encoder, pretty standard, nothing special in here. And in this case, we're just building a Siamese network. And in order for the Siamese network to work, we need two inputs. So these are our pairs. Run them through the same encoder to get representations, which are hopefully similar for similar pairs. And then we calculate our distance. In this case, we are taking the squared sum of differences. This means L2 loss, L2 distance. And on top of it, we'll just add one dense layer to get a probability out of it to denote whether pairs are similar or not. And then when we train the network using our loss function, we will compare this probability against our value, our label, where we say, hey, this should be in the same class or not in the same class. And this approach is, despite being so simple, it achieves 92% speaker verification accuracy on the Libre speech dataset already. So you can imagine that if you tune your network and use a better architecture, you can quite boost the accuracy a lot. Okay, now for these similarity learning approaches to work, especially in a deep learning setting, you need lots of data. It's a very general approach, and if you've got the data, it's probably the best you can do, state of the art today. But quite often you just simply don't have this data available, or you're not allowed to use it, or there are already historical other approaches available there that you can use that are good enough that it wouldn't make sense to reinvent the wheel. And typically examples for this are fingerprint and iris recognition. So for iris recognition, so just for an introduction, there's a picture. So if you look at this, you can sort of see that this has got these sort of features. You can sort of start to imagine how you might create features here that are enough to discriminate between different eyes, right? So you've got, in a way that for face would be difficult if you were to do it by hand. Here you probably can do it by hand, because if you look at this, well, sometimes these little features repeat more frequently than at other points, so even just using frequency information in here is probably quite a good guide
or quite a useful feature. And in fact, this is exactly what is done. People use something called Gabo filters, which are essentially localized Fourier functions on the iris to extract features and then compare this against each other. So in more detail, there's an open source package that we used for this called Osiris, and this implements this. This is a picture of my eye. And if you let Osiris have a go at it, it first finds where the iris is, cuts out the pupil, and it tries to mask any areas that are not part of the iris. So part of the eyelid that covers the iris, you don't want that in your feature recognition, because it will have different features. It will not be reproducible. Same with the eyelashes, and in fact you can see here it's the segmentation algorithm finds some of them but not all of them, so there's clearly still some scope for improvement there if you were to look to improve the system. Then next, this strip is cut open and projected onto a normalized rectangle. This is sometimes called the Dugman rubber sheet method, I believe. But really, all it is it's a projection from this ring onto a rectangle of standard size. And I suppose the biological intuition behind this is that no matter how much the pupil is dilated, after projection onto the normalized strip, the features will still look the same or similar enough for re-identification. And so when you then apply your Gabo filters to this strip, this normalized strip, what you end up with is the sort of pattern you see on the right-hand side. In fact, it's 6 different filters, so it's 6 strips on top of each other. And what you then can do to compare 2 eyes is that you have a predefined number of points where you will compare your 2 eyes. You ignore any areas that your segmentation algorithm says are not the iris, and you simply count the differences between your 2 eyes. So a score of 0 means perfect match. And yeah, you obviously normalize by the number of points that you compare. So a score of 1 means every single point you compare is different, which never happens. But yeah, so a small score means they are very similar. Okay.
Okay, so let's talk a bit about the software and the models you can use. So there's quite a lot of models out there. There's a model suite for TensorFlow, for PyTorch, whichever framework you would like to use. And we've seen that the approach can be applied to nearly any kind of data. And for speaker verification, you could also try out things like the Cognitive Services API from Microsoft. But we found that the results were very poor. So some people have like this general voice, which will always be verified as being you. So this is probably a bad thing, and you should build it yourself. Okay. And then there are classical machine learning things out there. For fingerprint identification, there's the automated fingerprint identification system, and there's an open source implementation for it. Fingerprint works a bit differently than iris, because in fingerprints you've got other kinds of features, like those ridges, you've got bifurcations, you've got little islands, things like this, which are quite different to the frequency patterns found in the iris. But for the iris part, you can really use the Osiris package, which provides you with pretty good results. Maybe you should Dockerize it because it's written in C and C++, and you need to compile it, and somehow you need to isolate it in an environment where you can rebuild it. Okay, so let's have a little demo time. Or do you want to add something?
No, let's play.
Okay, let's play. So let's play around with the identification app. So first of all, we said this must run on a mobile device, so we wrote a little web app for it. And now I could just put my face into where it belongs. Then I can hopefully register myself, and the service is running and registered me. And as a little check, if I now do the comparison against the image I just captured, the distance should be 0 because both of the images are essentially equal. So I've got an idea of what is it? It is E58 something. So if I do this again, maybe even under different lighting conditions, yeah, let's place my face like this and hope for the best. Okay, how about my glasses? So let's capture a picture without glasses. So you can see here the difference is under 1, and 1 is this part where we discriminate things between being similar or dissimilar. So let's just try out without my glasses. Okay, let's just put my face in here and identify myself. Oh no, I registered. Oh, that's bad. But we've got this E somethings.
Yeah.
And E something is already 1.08, so it's slightly above our threshold. So each value that is not really, that is somewhere around the score of 1, you cannot be very confident. Things that are pushed apart furthermore, you can be pretty confident that it's not the same.
If you want a bigger score, you can take my face if you want.
Yes, we could, for example. Yeah, but we can also compensate for this fact. So do we have the comparison against E something? Yeah. So the score is bigger now, yeah?
That's
the score to my ID. Yeah, it was E something. So the score went up from 1.08 to 1.28. But if you want to compensate for facts like wearing glasses, not wearing glasses, different lighting conditions like good light, natural lighting outside, very unnatural lighting, darkness where images tend to be much noisier, you can use low-shot learning. So because of this, you can also take multiple images and register them. And so then we can compare against each of those images which were taken and just take the best match, if we have one. So you can compensate it by doing low-shot learning. Okay. So let's go on to faces. Do we want to? We've seen faces, but we thought that Emilia Clarke from Game of Thrones and Robin Williams would be a good example to measure similarity. And in there we could already see if we're taking 2 images of her and then take a third comparison image, the score will be closer for one of those images. Actually, but we've seen this in the little demo before, so we could probably skip it. So let's go over to fingerprints. For fingerprints, when you process them in a classical sense, you need to have a very controlled environment. So fingerprint scanners are specialized pieces of hardware where you put your finger onto it, and there's a light source coming from a specific angle, and you also capture the image from a specific angle to avoid reflection, to have very controlled light in there, and then you need to get to a black and white image, essentially, to grab these features like the rich endings, bifurcations, and the stuff. And therefore, because you engineer this, you want to have matching histograms, so it should be really controlled. And you can use operations like erosion or dilation, even with directional filters, to modify how strong these ridges should be. And then you get an image like this out of it. So fingerprint recognition is not really integrated in the app right now, but we can try to compare some fingerprints in here. We've got a little API for this to integrate it into any kind of app, even after the prototype. So let's not take irises because it won't work. Let's take our probe of the fingerprint. Let's also select, first a good match, maybe, and execute it. And we get a score of 99 out of it. So APHIS has scores that are documented like this. Everything that is higher than 50, this could be a reasonable threshold, is considered a match. Everything below it is considered not being a match. So when we now take a bad example to compare against, so this fingerprint is clearly different, we'll get a very low score of like 2.2. Okay, so this essentially works pretty well. So for faces, we use low-shot learning to improve conditions. For fingerprints, classical approaches in controlled environments work very well. And for iris recognition, we also need very controlled environments because...
Yes, for iris recognition, as we've already said, it's crucial that you're able to segment any parts that are not part of the iris, like the eyelids or the eyelashes. But also, and this is a problem in particular the right picture here, which is Mathias's eye, I believe. Obviously, if you simply try to take a picture of the iris in an office or even outside, you will typically have a reflection of something in this eye. And this will completely cover the actual iris features that you're trying to evaluate. So I think real iris detectors sort of use some sort of tube to shut out any light from outside and have an LED ring inside to light up just the eye as it should be. We didn't have that, but we can still make reasonable, show that it works reasonably well. So the first two eyes here that we want to compare are my right eye, I believe, and the third eye is Mathias's left eye.
So let's register this. Maybe under the ID BCA something. We take the iris, we take your eye, register it under the ID.
Okay, so we've got an
okay,
eye.
it's registered.
So it's
And by the way, we're using unique identifiers, but they are anonymized because basically we want to have an anonymous system where we don't get regulatory problems. But if you want to capture some metadata, you can connect those IDs to some personal metadata if you want to. But it's better to have a service that is anonymous by default and build your mapping later on, because you've got all the flexibility. So let's try this out. We'll just take your other iris, and the threshold here should be around 0.4, if I see it correctly. It's documented,
yeah,
probably.
This is not something we've found in the actual documentation of Osiris, but by trial and error, we sort of worked out that anything above 0.4 seems to be, is rarely a match, and things below tend to be matches. Yeah.
Yes, and you can already see that our environment was not that controlled,
Yeah.
so the values are really around the 0.4 here,
Yeah.
which is kind of a bit undesirable.
So it still indicates a match, but partly because of reflections in the eye, but also because the segmentation of eyelashes and eyelids weren't as good as they could be. The score is still fairly close to this 0.4. Although, as you can see, the difference to Mathias is still significantly bigger.
Yeah,
So, yeah, what do we conclude from, or what have we learned from this project? Well, one thing is the similarity learning, this concept that underlies so much of the modern approaches to biometric identification systems, is a very general approach, and it can, given enough data, it can essentially be applied to any biometric data that you could find. The problem tends to be finding the data in good enough quality and in good enough quantity. The second, we've just made this point, then, obviously, often you don't have the data, then classical approaches can still be very good, especially for things that have been around for a long time, that have been developed for a long time, like fingerprints or irises, where it's relatively straightforward to construct discriminative features. And finally, there's a lot of good software and good models out there. To build these prototypes, we talked a lot about the concepts and the models and how you train them. Really, for these prototypes, we didn't have to do any of this. There were finished open source software is out there. Even trained models are out there that are very well trained, and so you can sort of try things out very quickly if you want to and have to.
So we also provide you with some sources and papers where you can have a good read or can find data available. And the key message is really that if you want to take a step further, you should definitely gather good data. Maybe you cannot gather it from a start. Maybe you have just to write your registration and identification system, register a few people, then you've got data available, and then you can train on your own data. So you need to have the feedback with the data in the field, because you cannot gather it via other sources maybe. And when you do and you gather your data, deep learning approaches are really a good way to go, because you don't need to do this feature engineering by hand. And if you have enough data and lighting conditions and variation, those tend to be more robust than the classical approaches. But if you can have a really controlled environment, like with iris scans on doors, for example, you can just stick with the classical methods, because in a controlled environment, they've got phenomenal accuracy. Okay.
Mathias, Thomas, thank you so much for these insights into your endeavors. And if there are questions, yes, there are questions. You can answer them right away.
You were talking about the difficulty of getting data, and now in the end you said you can just start the thing and then you will gather or accumulate data basically by having first customers registered and then going from there. How would you then, I mean, kind of prohibit a certain skewness in your data? Because if you start, I mean, there might be some sort of prejudice or whatever that you train into your system then. Yeah, so there are also biases in the data that is available right now. If you have a look at the faces databases from celebrities, you won't find black women a lot. So most of the systems trained on this just discriminate black women. So this is a bad idea, and you really have to look into your data set and see if there are any biases. And you could, for example, use metadata, like where does one come from, the ethnicities. And you need to balance it to get a good model.
Yeah.
And you need to visualize, try out.
I think the face example is really, illustrates this really well, because yes, we have got big data sets, but these tend to be of celebrities because those pictures are available. And celebrities in the Western world tend to have a certain look. Yeah.
Any other questions?
Thanks. Regarding the center loss, wouldn't it be possible to just use the angle when you take the point where all the classes meet as the origin, and then use the angle to consider which class or what's the distance is?
Yes, this is called angular loss. There are cosine losses, large margin angular losses, and nowadays these are really employed and get the top accuracy.
Yeah, this is done. Yeah.
So there's an arc phase model, for example, which gets this 99.8% accuracy. Really?
Yeah.
The idea, it's a bit different from the center loss. The center loss pulls together the representations, and the angular loss introduces some margin so that you can really discriminate classes well. And by increasing this margin, it also pushes together the other data within a very constrained angle.
I mean, it's slightly more complicated because, okay, we've shown these nice 2D embeddings of MNIST, right? In reality, 2D embeddings are rarely enough, right? So you've got higher dimensional embedding, and then finding angles is not quite as easy, but yeah, angles are being used.
Further questions? All right, then again, thank you very much. And
thank you.
Thomas, for you, we still have a little something. Matthias already got his little something.
Oh, I see.
So thank you much
thank you
for the talk. And thank you everyone for listening, and enjoy the rest of the day, of the evening.